In our previous video, we actually started the process of testing for concavity in a process that was pretty similar to the first derivative test for finding relative extrema. But we started the process of actually looking at the number line and seeing where our second derivative changes sign. So I want to go further into that, but I want to formally lay out how do we actually test for concavity. So we're going to actually find the second derivative, and we're going to put in values for C such that that second derivative is either 0 or undefined on our number line. We'll do the sign test where we draw the number line and we actually check to see where that second derivative is changing signs. And we're going to just check to make sure that if f prime of c exists and we see a sign change at the point where f double prime of c, or a second derivative, is either 0 or undefined, then we will call that an inflection point. Okay, so let's try that. So let me actually start with number 4 first, since the previous one is actually a problem that we will do using a calculator. Let's start this one first. Okay, so first things first, we are given the function. We're told that that function is x squared plus 1 over x squared minus 4. And we're just for just kind of convenience sake, we're given the second derivative. Now, let's check to see, is there any place where this function is undefined? Let's actually look at the domain of this function first. The domain of f of x, let's just write that. The domain of f of x looks like it's all real numbers, except where? Except x can't be equal to positive or negative 2, because that would cause that function to be undefined. That's going to be important for us. Now, let's look at our second derivative now and ask ourselves, is there any place where that second derivative would be equal to 0? And if you're looking at this carefully, if we even just take the numerator, for example, and set that equal to 0, this gives us 3x squared is equal to negative 4. Well, x squared is equal to negative 4/3. Well, we see that no value of x would ever cause this quadratic to be negative. So this can never, our second derivative can never be 0. However, that's not the only condition that we could have for a possible inflection point. Is there any place where now our second derivative would be undefined? Well, we then take our denominator, because we know that our denominator can't be equal to 0, set that equal to 0. And looking at this here, are there any values where this function now would be undefined? Also, positive and negative 2. Okay, well, here's the deal. There are places where this function can be, where the second derivative can be undefined, but it turns out that's exactly where our original function was undefined. So if we kind of draw this number line here, just to kind of visually lay this out, for example, if I were to draw a number line here, at negative 2 and 2, although I might be tempted to call these inflection points, what's actually happening here is there are vertical asymptotes because the function is undefined there. So we can see that if you were to go ahead and try plugging in values within these intervals into our second derivative, we would see that this is going to be positive, this is negative, this is positive. So this goes concave up, concave down, and concave up. However, even though there are changes in concavity, there are no inflection points. So I'm going to write that. There are no inflection points. In fact, there were no possible inflection points because there were never any values. F prime of x can't be equal to 0, can't be equal to 0. And the only place where f double prime of x is undefined at our domain restrictions. So the only places where there could have been inflection points were where there were vertical asymptotes. So all we can do is state the concavity regions, or intervals, I should say. So it's going to be concave up from negative infinity to negative 2, and concave up also from 2 to positive infinity. It's going to be concave down from negative 2 to 2. Okay? All right, let's try this next problem here. Now this problem is going to be pretty heavy with the calculator, so if you have a graphing calculator on you, go ahead and give that a go. And I also think I probably need to give you an interval here from negative pi to pi. Okay, now this is going to be a graphing heavy problem. So for this, the main thing I want you to do is I want you to graph the second derivative. So graph f double prime of x. which is negative 4 sine 2x minus 1, okay? Go ahead and graph that. But what you should get are a number of different inflection points here, and I'm just going to list them. This is kind of hard to get across in just a video, but I do want to list them and provide them to you if you wanted to just quickly check your answers. So you have 1.697, negative 1.690, and I believe there's one more. It might be a little bit hard to see. Let me just write this, negative 4.796. So there should be 4. Okay. On top of that, where is this concave up? It's going to be concave up from negative 1.444, negative 1.26, and then positive 1.697 to pi. And it's going to be concave down from negative pi to negative 1.444 and negative 0.126 to 1.697. Okay, so that's something more for you to determine the concavity practicing using your graphing calculator. Now, one other utility of the second derivative is that we can actually also use the second derivative to find extrema of a function. So we're not limited to just only using the first derivative test. We can actually use what's called the second derivative test. Now, to be clear, the second derivative test is not for inflection points. Okay, it is not for inflection points. Rather, it is to find extrema. So this is pretty logical when you kind of think about what we've been able to put together. Suppose a function had a critical number at x is equal to c. So let me just plot x is equal to c. And you know that the second derivative is positive there. Well, what do we know about the graph when the second derivative is positive? Well, it means that function then is concave up. So if you know your function is concave up because your second derivative is positive, and you have a critical number at x is equal to c, then what type of extrema must be guaranteed? This has to be a relative minimum. Similarly, if you had a critical number at x is equal to c, and this time your second derivative is negative, therefore it's concave down, now that tells you you have to have a relative maximum there. Well, what about when you have a critical number x is equal to c, and f double prime of c is equal to 0? What type of extrema would be guaranteed there? Think about that. And the answer is none. You cannot guarantee an extrema there. There may be an inflection point, but no guaranteed extrema. Okay? So let's actually try this with a problem here. So let's use the second derivative test, again, to find the relative extrema of the function. And let's try this problem here. Okay? So first, to find the second derivative, I'm going to need the first derivative. So f prime of x is equal to negative 12x cubed plus 12x. And I'm going to need my critical numbers. So before I jump into finding the second derivative, let's find my critical numbers. So I'm going to set my second derivative equal to 0. So this is going to be negative 12x, and I got x squared minus 1. So my critical numbers, x is equal to 0, and positive and negative 1. And because this was a polynomial function, there's no place where my second derivative would be undefined, so I don't have to worry about that. Now, what about my second derivative? So f double prime of x now is equal to negative 36x squared plus 12. So now I am going to evaluate my second derivative at each one of my critical values. Why am I doing that? Because I want to see what the concavity is at these critical numbers. So f double prime evaluated at 0. If I plug 0 into this, I get 12. So what does this mean? It means since this is greater than 0, it's positive, this was concave up at this point. So at 0, it's concave up, meaning we have a relative minimum here. Now let's keep going. What about the second derivative evaluated at positive 1? Well, this is going to be when I plug 1 into my second derivative, I'm going to get negative 24, which is less than 0. What that tells me then, this is concave down. Therefore, at this critical number, we have a relative maximum. And finally, at negative f double prime of negative 1, again, that should also give me negative 24, which is less than 0, meaning it's negative. So it's also concave down. So this also is going to be a relative maximum. So we can use the second derivative, so the relative minimum, to find our extrema. Our relative minimum is going to occur at 0, and I plug 0 into my original function. F evaluated at 0 is just 0. My relative minimum is going to be this function evaluated at negative 1 and positive 1. And I think in both cases, since my degrees are even, both cases I'm going to get positive 3 as a result. So we can just write this. So that's a really helpful test to have, because it allows us to find the second derivative, use the second derivative, I should say, to find relative extrema. And oftentimes that might even be faster than using the first derivative test. But more than anything, it's important just to understand the relationship between extrema and concavity.